We'll be looking at probability rules in statistics. So it says for any event, the probability of not A is equal to 1 minus 2A, or the probability of A. And that's the complement rule there that we see in example 1. The second one says for any two events, A and B, probability of A given B is equal to the probability of A and B divided by the probability of A. And then that is actually going to be considered the conditional probability of two events. Okay, so then we're going to look at independent events. And then if you look at events of A and B are independent if and only if the probability of A and B is equal to the probability of A times the probability of B. And that's when we're looking at whether something is independent or not. That's using the multiplication rule for independent events. So, what we're going to look at now is the complement rule. Just simply says, we've already talked about the complement. If it's A, then not A is the complement. How would we look at that? For example, suppose that the probability that a particular flight is on time 78/100ths. What is the probability that the flight is not on time? Well, we would simply say 1 minus 178, which would be okay, so that would be the likelihood or the probability that it would not be on time. A lot better chance of it being on time. All right. Example 2 says formula of conditional probability. So when we're looking at that, I think I may have called that on the first page of independent events, but it's not. It's of conditional probability. When a room is randomly selected at a downtown hotel, the probability that the room has a king-sized bed is 62/100ths, and the probability that the room has a view of the town square is 43/100ths, and the probability that it has a king-sized bed and a view of the town square is 38/100ths. Now, let A be the event that the room has a king-sized bed, and B be the event that the room has a view of the town square. What is the meaning of the probability of A given B? Well, the meaning would be that probability of A is that the room has a view. I'm saying with a view, and B is with a king-size bed, so the room with a king. Okay? That's what we're talking about. What's the probability of it having a view and a room with a king-size bed? Okay? So, now what we're going to look at is this, making this hypothetical 1000 calculate probability. So we're going to make it total 1, because we don't want to do 1000 because we want probability here. So what we're going to look at is that it has a view of town square is 43/100ths. So we'd say that would be here. It has a view of town square. So we're going to go ahead and write that in as 430,000ths. I'm sorry, that is not where that goes. That would go over here in the total. Okay. Now we know that the probability that it has a king-size bed and let's do this right here. King-size bed. There you go. Well, the probability that it has a king-size bed would be 0.620. Now we can go ahead and calculate these knots here, or the complements of A and the complements of B. Okay. Now the other thing that we know is that it's a king size and has a view, and that is 380 thousandths. Now we can calculate the remainder of the table. So this would simply be 0.050, and hopefully you do not have trouble with this. If you do, you need to be asking. Alright, now then, let's keep going. C says there is a formula to calculate a conditional probability. The formula for conditional probability is the probability of A given B, and that is the probability of A and B divided by the probability of B. Use this formula to calculate the probability of A and B where the events A and B are defined in this example. Now, what was A and B? Well, A and B, if we go back, is 380 thousandths. B is here, and the total of that is 430 thousandths. So that's what we're going to calculate. We're going to say 380 thousandths divided by 430, and that is 884 thousandths. Now, how does the probability you calculate using the formula compare to the probability you calculated using the 1000 table? Well, if we go back and look at the table, okay, how would we come up with the 884 by looking at this table? Well, use a hypothetical. This is what we're supposed to do here. What is A given B? Well, A given B is simply, if you would look at this, and this would have just been a hypothetical 1000, that would have been 380 divided by 430, and that would have equaled not 844 but 884. So if we had actually done it as a,
this should say 884.
Hypothetical 1000, that's what we would have gotten. But since we're doing, since we went ahead and done the probability, that is what we get. So D, how the probability you calculate using the formula? Well, it's the exact same. So you can use the hypothetical 1000 or you can use the probabilities. All right, let's look at exercise 1. It says a credit card company states that 42% of its customers are classified as long-term cardholders. 35% pay their bills in full each month, and 23% are long-term holders who pay their bills in full each month. Let the event that a randomly selected customer is a long-term cardholder be L, and the event that a randomly selected customer pays his bill in full each month. So right here, what I would do, I like Venn diagrams, and that's what we're going to do here for B. It says, what are the values of the probability of L? Well, L is long-term cardholder. The probability of that is 0.42. the probability that F, they pay in full each month, is 0.35. And then we would have the probability that they are a long-term cardholder and pay their bills each month is 23 hundredths. So now let's draw a Venn diagram. Okay? If we have, this is L and this is F, and that they are both, we've already said, is 0.23. So we've got to subtract that from, this is L and this is F. So if we subtract that from L, that gives us 0.19. If we subtract it from F, that gives us 0.12. Okay. Now, use conditional probability to calculate P, or the probability of L given F. Well, L was 0.19 and F was 0.12, but here's the and right here. So we're going to plug in 23 hundredths over what was F given F. Your given is what goes on the denominator, or given in the denominator. So you're going to say 0.35. Okay, and that's going to be approximately 0.657. Okay, that's the probability that L given F. Now, let's go to page 5. It says use the conditional probability to calculate P, the probability of F given L. Well, that's just right, the exact opposite, right? Oh, no. We need to say of F given L. Okay, so all that would be, yeah, that's just the exact opposite. We're going to have 0.23 over the 42 hundredths. And that's going to be approximately 548 thousandths. So which is greater? F given L or the probability of F? Explain why this is relevant. Well, F given L was, that's what we just had. So this is, okay, and the probability of F was 35 hundredths. So the probability of F given L. So why is this relevant? Why do we care? Well, the long-term card holders are more likely to pay off their bill at the end of the month. That's what that means. Okay, this is card holders not just card holders, but long-term card holders paying off bill, as opposed to ELF, where ELF is simply the event that a randomly selected person would pay it. So they're more likely, if they are a long-term card holder, to pay off their bill each month than just any randomly selected person to pay it off. So you want to keep long-term card holders because they're more likely to pay off their bill. Or you don't. Depends on if you're wanting to draw that interest and make money off of them. Okay. So remember that two events, A and B, are said to be independent if the probability of A given B is equal to the probability of A. Are the events F and L independent? Explain. Well, we would say they are not independent of P of the probability of F given L, because that is not equal to the probability of F. Okay? And it's the same thing of L given F, because it's not equal to the probability of L. And then we can also say that because the probability of F given L is not equal to the probability of F times the probability of L. So therefore, we would say that they are not independent of each other. For them to be independent, they would have to equal each other. That's what you need to remember. It's a little bit confusing. All right, let's go to number 6. Now we're using the multiplication rule for independent events. A number cube has a face numbered 1 through 6, and a coin has 2 sides, heads and tails. The number cube will be rolled and the coin will be flipped. Find the probability that the cube shows a 4 and the coin lands on heads. Well, because these events are independent, right? They don't have anything to do with it. Whether you roll a 5, it doesn't matter that it has no effect on you flipping a head or tail. Those have nothing to do with each other. We can use the multiplication rule that we've just learned. So, what you would say is, what's the probability that it rolls a 4? Well, there's 1/6 chance, right? And what's the probability of you landing on heads? Well, that's 1/2. If you multiply those together, you're going to get 1/12. That's the chances of you both rolling a 4 and flipping heads. Now, if you toss the coin 5 times, what's the probability that you will see a heads on all 5 tosses? Does the first toss have effect on the second one? Well, no, they do not. So we can multiply those together. So do it 5 times. And that's going to equal out to about, the probability would be, if you multiply those out. Okay, which that's equal to about 1 over, was that 32, 2, 4, 8, 16, 32. Yeah, 1 over 32. Okay, now if you toss the coin 5 times and got 5 heads, would you think that this coin is a fair coin? Why or why not? Well, this is what it's talking about here. What's the chances of that happening? About 0.03. Or that would happen 3% of the time. So it would probably be not fair. Your odds are not good. Okay, 3% is very unlikely. Okay. Number 7 says, if you roll the number cube 3 times, what is the probability that it will show 4 on all 3 rolls? Well, what's the chances of rolling a 4? 1/6. Does the next event depend on the first one? Well, no. So all we have to do is multiply those together, which would be 1 over 6 cubed, and that would equal 1 over 216, which is equal to about 5 thousandths of a chance. Okay, So if you rolled the number cube 3 times and got a 4 on all 3 rolls, would you think that the number cube is fair? No way. It is almost impossible. Okay? So now, suppose that the credit card company introduced in exercise 1 states that the customer is selected at random and the probability that that customer pays his bill in full each month is 3,500. And the probability that the customer makes regular online purchases is 8,300. And these 2 events are independent. What is the probability that a randomly selected customer pays his bill in full each month and makes regular online purchases? Well, we know that if they are independent of each other, all we have to do is multiply them together, because they don't have any effect on each other. And that would be about 291 thousandths. So out of 1,000 people, about that would happen 291 times. Okay. Exercise 2 says, a spinner has a pointer, and when the pointer is spun, the probability that it stops in the red section of the spinner is 0.25. Okay. So, if the pointer is spun twice, what is the probability that it will stop in the section on both occasions? Does it matter what it lands on the first time? No. So, it's not going to matter the second time, and we can just multiply those together. And that's 1/16, which is about 0.0625. That's your probability of that happening. Now, if the pointer is spun 4 times, what's the probability that it will stop on the section on all 4 occasions? Well, we would just multiply it by itself 4 times, which would be equal to 1 to the 4th power, which is about 0.004 times. Those likelihoods are not good for either one. This happens about 6% of the time, and this one happens absolutely never, almost. Okay? If the pointer is spun 5 times, what is the probability that it never stops on red? So here we're talking about it never stops on red. So that is not 1/4. Well, what is 1 minus 1/4? That's 3/4. And it's going to be spun 5 times. So we're going to multiply that together 5 times. Which is the same thing as saying 3 to the 5th power over 4 to the 5th power, which is about 0.237. So that's a lot more likely that it's going to not land in red 5 times in a row. Okay? And that is it for this lesson.